right, start recording. Go through a few of these in quick succession, and probably one that nobody had unless you peeked ahead. So we knew that we wanted to add pin C to pin D and put it in 90. So as just a comment here, 90 equals pin C plus pin D. That's kind of what we want to do. So here's option 1. Since we know that pin C is absolute address 29, I should have it right in front of me here. It's plus pin C 20, 06, 26. I got to just write it down here. 06, 09. Those are the IO addresses. I could say LDS, which is load from data space, R1 $26, LDS R2 $29, add R1 R2 STS, and then I got to pay attention to my order here. Data always flows from right to left, so the thing on the left has to be the destination. So the destination is 90. Okay, and then R1. Again, the 1 is important because the data flows in add, it flows into R1. So everything is flowing from right to left. That's one way of doing it. Not the best way. It's actually the worst way. Okay, way 2. Better. In R1 06 or $06, could just say 6. In R2 $09. Add R1 R2 out. Excuse me, not out. No, still STS. $90 R1. Better way. Okay, this uses in and out, which are faster. And fast is good, especially if you're going through the trouble of building an embedded system. You want it to be fast. So this uses in, which is much faster than LDS. You still have to use STS because you are putting it to 90. All right. Notice, by the way, that there's a difference in the addresses that we used. Here we used its absolute address. Here we used its IO address. Okay, you ready for the best way? You are not prepared for the best way. Best way. In R1, pin C. In R2, pin D. STS 90. Oh, excuse me, got to do the add. Got to do the add. R1, R2, STS 90, R1. Now, I don't expect, how many people, did anybody have this solution? Did you use the pin C and the pin D? All right. So this was sort of a hidden trick here. If you had gone through the reading, you might have seen this. The reason in is so useful is because the assembler defines the word pin C, the text in pin C, to be 6. It defines pin D to be 9. So you don't have to remember. You don't have to have this thing around for this kind of stuff. You just say pin C, pin D. All right. Now, once we get to chapter 4, you'll know what pin C and pin D do. Okay. But 3 different ways. This is obviously the preferred way. It's the easiest to understand. There's no hidden stuff. If I didn't have this comment here, for example, and this is getting a little messy now. If I didn't have this comment, you'd have no idea that I was referring to pin C, right? But there's a reason that I wanted that 26. It's because I wanted to deal with pin C, okay? So, checkpoint. This is something to go back and look at when you're studying. Do you understand the following instructions? LDI, add, LDS, STS, in, out, increment, and decrement. Those are the basic ones that we talked about. So what do those mnemonics mean? What kind of operands are they? Are they immediate? Are they registered? Are they addresses? What are the limitations of these operands? Can the immediate value be 10,000? Does it have to be less than a certain value? Are there certain registers we can't use? Okay. On to more general things. Can you define what memory mapped I/O is? Can you write it down? How many general purpose registers are there in the 328P? How many special function registers? These are the ones we have to use in and out. How many special function registers are there? On the 328P, where does RAM start and end? How big is the address bus on the 328P? How big is the data bus on the 328P? These are things that I didn't specifically tell you, but you can easily figure out. All right. We're running out of time here. I'm panicking a bit. An assembly program consists of two things, and we've talked about one of them, instructions. Okay, LDI, STS, so on and so forth. The other thing it consists of, though, is directives. Directives, also called pseudo instructions. Okay, so directives don't go on the processor. They are actually instructions to the assembler that tell the assembler how to compile things into machine code. Things like instructing the assembler how to treat custom names, like pin C. That's done with a directive. And they make a program more readable. Those are the two main reasons we have directives. More readable, okay, is the big one. So how do we make things more readable? Well, let's start with a single directive. Equate, .equ. If you say .equ, you then provide some human readable name, the equal sign, and some value. Anytime from now on when you use name, whatever it is, it will be interpreted as whatever the value is. Super handy. Things like constants, things like fixed memory addresses. Okay. Set, it's there. Avoid it for now. It can cause weird side effects. Once you equate something, it's like that forever. With set, it's almost the same as equate, but you can change it later in the program. And I don't recommend doing it because as you start copying and pasting and moving things around, suddenly it's set up here and it's changed and you expected it to be the old value. It's just a big nightmare. Equate, though, super useful. Okay, and we'll go into that quite a bit. EQU. All right, that is, okay, what is it good for? It's great for constants and fixed memory names. It's terrible if the data that you want to use that special name for is changing data. Never confuse it for a variable because it can't change. It's not for changing data. It's great for constants only. And those constants can be memory addresses. So .equ is the name of it. The next one that you're going to use almost every program, in fact you must, is the .include directive. You include a file name. Basically it copies and pastes whatever's in that file into yours. In almost every program you're going to have this line, .include, open quote, m328p def.inc, .include. And all this file is, you can open it up one of these days if you're so inclined. It just defines what pin C is, what pin D is, what port D is, what, all of these names. It defines all of them as the address. The only caveat here is it defines the I/O addresses, the special function registers, as their I/O address. So if you're going to use in and out with those names, if you're going to use the name pin C, you must use in and out. You can't use STS. Okay, so there's .equ, .include. Then we've got a whole host of them. We're going to go through these one at a time. .org, .dseg, .cseg, .byte, and labels. I'm going to cover all of these, but I want you to know that they all exist beforehand. Any line in your assembly program has 4 parts. If it's in brackets, that means it's optional. Okay. So as a minimum, you must have a mnemonic, LDI or STS. Some instructions don't need any operands. That's why it's optional. And a comment, optional. Okay, so a basic one might just be LDI R17, 10. Perfectly legitimate line. Doesn't have a comment, doesn't have a label, but those are optional. Now, when you start writing instructions, you start writing on line 1. When you assemble this, it's going to shove it into program ROM. And it does that starting at address 0. Starts at address 0, and every instruction after that goes in the next location. Address 0, address 1, address 2, and so on, until you've exhausted all of your instructions. These compiler directives or assembler directives allow you to tweak where stuff goes. So let's go through each of these and how they relate to each other. First off, let's pose a question here. I did not want to hit that button. I wanted to hit this button. So in a Harvard architecture, right, we've got our RAM bus over here. We've got our ROM bus over here. ROM, we start putting in instructions at address 0, and then we start putting things in. What if, for some reason, I wanted to put information after a space? So put blank space here, and then I wanted to put something there, an instruction, some fixed data, something. We entered the .org instruction, or compiler directive. It's called the origin directive. All it means is if you say, do I have an example here? I do. I have a really good example. Oh, good. Here's some code. This is exactly what you type in to your editor. .org0 means that it's going to put this instruction right at 0. I have not shown you the map to get from this instruction to E205, but trust me, it's legit. Then I put another origin directive, origin 07. That means that this instruction is going to go at 7. Unused addresses are by default filled with 0. This is not so useful when you just have code, but when you have fixed data that we get to in chapter 6. So that'll be Friday, I think. We get to chapter 6. The fixed data can be put anywhere you want. So it's helpful to do that. Usually, you will have labels also associated with this. We'll get to labels in a second. All right. Now, .org tells you where you want to put stuff. But we do have a Harvard architecture. And what's the defining feature of a Harvard architecture? There's 2 buses, one for data, one for code. So we actually have 2 more assembler directives to tell us where we want to put stuff. Do we want to put it in the code segment? We would say cseg, that puts it in ROM, or the data segment, which puts it in RAM. And the thing here is you can't actually put executable instructions into RAM. You can only reserve space. Okay, this is the equivalent of defining a variable. I'm going to make a variable called my storage, and I've got it right here. My storage, it's going to be 4 bytes. And so that's the last assembler directive in this related group. .byte says reserve space for 4 bytes here. We'll use it somewhere else. So this is a perfectly legitimate program here. .org0, it defaults to the code segment. So we put LDI R16 10. Then we change over to our data segment and we say, all right, at address 100 of our data segment, which, by the way, that's the start of RAM. It's the green thing from before, that green box. It's the start of the actual physical RAM. I'm going to reserve 4 bytes, and I'm going to refer to it by a label. The label is called my storage. It can be called anything. It can be called Bob, okay? It doesn't really matter. You can call it something descriptive like my variable so-and-so. Then I switch back into my code segment. And now I get the best of both worlds. Anytime you've done a label, it's almost as if you've done a .equ with it. So I say LDS R17, and I can use the word my storage to refer to this block in RAM. Getting good at this requires that you just continually do it. There's no other way. Like, I can explain it to you, and you can say, okay, I get it. Labels equate to addresses, .byte reserve space. Origin tells the assembler where to put stuff. But until you start combining this together, it's going to be sort of out there, okay? But now we've got all of the building blocks to make any kind of program we want, all right? So I want to talk about, let's say you have a program, what happens when you go from the program assembly code to the chip. It's not a very complicated process. You go from your assembly code through a program. The program takes in assembly code, it outputs machine code. It's called an assembler, and typically your assembly code has an extension of .asm, but it's just a plain text file. And here is the machine code file. It's usually called .hex. It also outputs a bunch of other things. It can output, if you have electrically erasable programmable memory, which is something I didn't talk about. It's a non-volatile type of memory that can be modified. It'll output a .epp file. Both of these files will go into another program called a programmer. Its job is to actually take these files and put them into the associated memories on the chip. So this this chip right, or this development board, the chip on the right, the tiny one, that's actually the 328P. The chip on the left, the larger one, that's actually the programmer. So data comes in on the USB port, is interpreted by the programmer, and stuff ends up inside the 328P. And so it can program both the EEPROM and the program ROM, the flash ROM. These two files here are called diagnostic files. And I've spelled it out. The map file shows assigned values of labels. The listing file combines your assembly file with the machine code. So when I said that this stuff really was the assembly code and the machine code together, I stole it from the listing file, okay? And it's really useful to look at these diagnostic files to see if things are going wonky. All right, here is your homework. And what I'll do, you know what? You can have the answers. You can absolutely have the answers to check yourself. Here's the homework. I want you to ignore the green stuff, okay? Now, it's on YouTube. You can go back and you can look at it. That's fine, okay? I want you to take this assembly code, and here is your map. Okay, just like we did at the beginning of class, but this is a real processor now. Here's your map. I want you to take these assembly instructions, and I want you to give me the machine code associated with them. Just practice it. Things that you're going to see that are not probably what you're used to. Here, the K is split. Okay, it's 8 bits of K, but they're split. The ones on the left, those are the upper bits, the upper nibble, and then there's the lower nibble. Okay? Some instructions are actually 2 locations long. Okay? So actually, you'll see here, I've actually labeled the addresses 0, 1, 2, 3, 4, 5, 6, 7, 9. That's because STS takes 2 instructions. So that's something to consider. You'll notice that D spans like groupings of nibbles. That's okay. It's just 5 bits of D. That's your homework. Okay. is to hand assemble that. Chapter 2, slide 70. Let me just look at one thing here. Hold on. Book slides. Chapter 2, slide 17. How important is Chapter 2, slide 17? It is not important. We will not even be doing that. Okay, so we're going to skip ahead to the checkpoint. So this is the checkpoint. I think this is the end of Chapter 2. Am I right? We did make it all the way through Chapter 2. Okay. So checkpoints. What assembler directive should always precede the .byte assembler directive? They work in concert with one another. What file name should be .included in every program for the ATmega 328P? What do the .cseg and .dseg directives tell the assembler? What file will tell you where your labels point to? The label is always an address. So what file can you go to find out what label equals what address? What file will show you human-readable machine code with assembly annotations? And then two more things. Can you do this? Can you hand assemble sub I R1810, an instruction you have never seen before? But you can look it up on this. The opcode is on the left side, all right? And hand disassemble 7777. I have no idea if this is a valid instruction. I made it up. I'm interested to see what you come up with. I haven't tried to do it, but it works in reverse. You have to find 7 as part of the opcode. It's in hex, so just look at the nibbles. 7, by the way, is the nibble. 0, 1, 1, 1. So that's your checkpoint. So your homework, which I will collect, is hand assemble this. Okay. Now, you can absolutely go to the YouTube video before I erased this, and you will be able to give me a correct answer. You will be promptly shooting yourself in the foot. That's your prerogative. I would recommend doing it without looking at the instructions first. Okay? Do it completely through, then check it. If you're wrong, use that as a, where did I go wrong? Then erase the answer again and do it again. Okay? It's only, 8, 9 instructions. Okay? So I was nice to you. I pulled them out here, but you can also use this. Might be worth it. It might be worth your time to try and do it with this. Okay? Woo! We made it. All right, questions, thoughts on the pace, thoughts on anything. This is my first time teaching a 5-week course, so I want you to get something out of it.
On Friday for lab, but we're going to do it more than one lab.
No, I thought about that. That sounds torturous. There's not going to be any pre-lab. You guys are getting off easy. It's going to, well, except you have a semester project. So we're probably going to be doing cookie cutter labs. But after you're done with those cookie cutter labs, you're going to want to start thinking about your project. Okay, so if you go back to the syllabus, the last week, so we have a review on the, we have a exam on the, this is something worth talking about. On the days that we have exams, the first half of the class is going to be review time, and then I give you the exam. So it's like when you're done with questions, I give you the review. So the last week, though, is 11th, the 15th, and the 16th. You're just working on a final project. The final project is going to be some kind of a thing that has some output and some input and uses the processor. Something that it can be pretty and blink things, blink LEDs. It can use sensors. It's got to use a couple of peripherals. We'll talk about all this on Friday. It's going to be done as a team. So you will be doing teams, groups of 2. Do you want me to assign groups of 2 randomly, or do you want to choose your groups of 2? Hands for assign randomly. Hands for choose your own. Okay, well, 4 people out of 14 voted, so I guess you're up to yourself. You got to choose a group by Friday, group of 2. Your project will be done as a group of 2. I will be signing out all the stuff. There's only 7 groups. There's 14 of you total, right? 2, 4, 6, 8, 10, 12, 15. Well, I'll be looking at the attendance, I'll tell you. What was I saying? Everything's going to get signed out to you. So you can, since there's only 14 of you, I can absolutely sign out everything and you can keep it for the whole semester. But that means that you, I guess, fail if you don't return it. Let's go with that. You fail if you don't return it. Processors, peripherals, everything. Like, you can hang on to it. You don't need, those of you who've been with me before, don't need an analog discovery. We have installed analog discoveries into 18. Well, you know what happens. You can still use yours, and that's fine. You're welcome to. You can actually plug yours in and use 2 at a time if you want. But that's a thing. The other thing, last bit of business, then we can go for the day. If it continues to stay this warm, I may move us to a cooler room, like with AC that works. It might be across the hall. It might always be in 217. Anybody have a problem with that? All right. That's it. All right. I will post these. I don't know how many videos.